Hello to you in the next video. Today we will deal with the domain of functions. And before we start, I would like to discuss with you a few things, namely, what we will encounter here during this. There will definitely be shortened multiplication formulas. And now a quick reminder of the basic second-degree formulas. First of all, we have to remember the formula for the square of the sum and difference. It looks like this. There will always be the square of one of the elements, plus the square of the second element. In the middle, depending on whether there will be a plus or minus in this place, there will be a plus or minus double product of these two elements. For example, I will give x minus 3 squared equals x square. 9, because 3 to square is 9, and double product in connection with the fact that there is a minus, the result on the minus. 6x. So when we see something like this, or something like this, or something like this, we have to be able to change one into the other. In the sense when we see, we have to be able to write this part. And when we see such a record, we have to know that this is it. It will be 100% useful to us also. And here, in determining the domain of the function, another second-degree formula that we have to remember is the so-called difference of squares, not only x. Let's take our a because x will be later in the domains. That is a squared minus b squared equals a minus b, a plus b. So difference of squares is written as the product of the sum and difference of these two elements. That is, in one of the brackets there can be minus in the other plus. And what's interesting, the order of this notation does not matter because multiplication is commutative. These two formulas you have to remember, and in fact there are 3, because here in the first one we can do it for the square of the sum, or the square of the difference. If there is a plus, then here in the plus formula. If there is a minus, then here in the minus formula. Okay, once we know these formulas, the next rule. Let's imagine a function. Let it be the function gx. Our function will consist of the numerator and the denominator. In the numerator, we will have 1. And in the denominator, we will have some function fx. And this can be very different from what will be here in the denominator. It can be an ordinary linear function, that is, some linear factor. It can be a quadratic function. It can be a polynomial function, and so on and so forth. However, what you need to know about this particular notation, you have to that we know that f must be different from 0. So that is like the first condition. If we have such a record that there is some function that has some polynomial in the denominator, we have to remember that this polynomial cannot equal 0. This means that we have to calculate the roots of this polynomial, that is, solutions. And these solutions of this polynomial cannot be inside the domain. That is, we have to eliminate all solutions of this denominator. Then let's imagine that we could have a function of the type h from x. For example, this function would look like this. But it would be the root of some function fx. And here we have to think about how roots work, because this is a square root. Roots of the second degree, namely, we can only use such roots to extract positive numbers and possibly 0, so in this case, our function f has to be greater than or equal to 0. And standardly in this place, there can be some linear function, some quadratic function, we have to calculate its roots and examine the interval in which this particular function takes positive values and zeros. And this interval is then the domain of our new function. And let's imagine some function k from x, which again looks like fraction. At the top there is some number, some function. What is most important? It does not affect the domain. And at the bottom, there's the square root of f from x. And this is a very similar situation to the previous one. Here with the second principle, except that due to the fact that this function is in the denominator and is under the square root, firstly, it cannot be 0. And secondly, it has to be greater than 0. So this information with 0 is mutually exclusive. So this function can only be fx greater than 0, cannot be equal, because it is in the denominator. So as if this third condition is a compilation of the two previous ones. If something is in the denominator, it cannot be 0. And if something is under the square root of even degree, it must be greater than equal to 0. Usually in tasks, we will have a function under the square root of the second degree. Although a function could also happen under the fourth degree root. But we would solve it in the same way as here. So let's move on to our tasks. The first task is quite simple. Remember, we will use this from the fact that this cannot be 0. So let's write x minus 3 equals 0. So x cannot equal 3 because after adding the 3. It looks like this equation. This is the inequality as follows. So the domain of this function are the numbers x belonging to real numbers, but without the single element set 3. In this way, we write it as differences of sets. That is all possible real numbers without the 3, because the 3 put in the denominator would give us 3 minus 3. That is 0, and we know well that we cannot divide by 0. So let's move on to the next task. Here we see that the denominator firstly has to be greater than 0 and not equal to 0. We will write it this way, and if we have such a situation, then we extract this function from the root. We write x minus 1 greater than 0. We solve very similarly to the previous one. We can add 1 to both sides. And it turns out that x is greater than 1. Then we can write that the domain of the function is x, belonging to the interval from 1 to infinity. Wait, I'll draw better, infinity. First of all, why is this bracket open here? Because 1 cannot be in the domain. Why? If we put 1 in this place, we would get 0 in the denominator. And we can't have 0 in the denominator from the first principle here. Secondly, why don't we close infinity? Because infinity has no closure. We can't close any number in infinity because simply, even if we invent a number, for example, 1,000,000, it can always be a number 1 bigger that is 1,000,001. If we invent a quadrillion, it can be a number 1 bigger. That is a quadrillion and 1, and so on into infinity. There is no number with which we could end this bracket, so we can't close the right side of this bracket. Let's move on to the next task. This time we have a little more complicated. But we have 2 conditions to overcome. The first one is, and I will write it separately here, that x plus 2 must be greater, equal to 0. Besides, x minus 5 has to be greater than 0. And let's pay attention to how we have written it here. The numerator is under the root. So in total, we can write that x plus 2 and x minus 5 under the root is the root of x plus 2 over the root of x minus 5. And written in this way, we can see that here we have a function consisting of two functions. At the top is the root of x plus 2. At the bottom in the denominator, the root of x minus 5. So at the bottom, there can be no 0, hence there is no greater equal to here. And at the top, there could be 0, because in the numerator 0, nothing interferes. So here we can solve it like this. Let's solve both inequalities simultaneously here. Let's add 5. Let's subtract minus 2, and we will get x greater equal to minus 2. And x greater than 5. If we have a problem with such tasks in which we have two intervals, we can draw a number line and mark both places, and then draw their graphical interpretation. That is, x are greater than 5. Firstly, we make the non-closure as an open circle. And all x have to be greater than 5. So this is this interval. Then we can do the same with minus 2. Only in this place we have a circle painted over. It means that minus 2 also belongs to this interval that we draw. And we also draw it to the right, because x have to be greater or equal than minus 2. Then we check where these intervals met. Met in this space. That is the domain of the function, or all x belonging to the interval from open 5 to open infinity. Why open? Because 5 belongs only to this interval. And here does not belong, so if we're looking for the common part of these two intervals, then this 5 belonging only to one of the intervals does not belong to the common part. That is, to the domain that is in the common part, we write that 5 is open. It means that it does not belong to the domain of the function. And the domain are all x from 5 to infinity. Let's move on to the next task. And here, if you look closely, we already have the first formula of shortened multiplication, which I mentioned earlier, which I warned you that this would happen. So let's move on. Let's do it such a trick. Let's go down here to the calculations. Here, let's transfer our calculations and continue. So we can see for sure that x minus 9, due to the fact that it is in the numerator under square root. It must be greater than 0, but x plus 3 cannot be 0. So x cannot be minus 3. And we will write it down in two brackets, that is, x minus 3x plus 3. Greater than equal to 0. Let's look at where this formula came from. Let's recall the formula for the difference of squares, that if we have something squared minus something squared, then we write it down in two brackets which are multiplied with each other with changed signs for these factors. And indeed, we have x squared minus 3 squared. 3 plus minus xx. I hope you see it. There may also be a problem with understanding what the interval is. I always draw a number line if I have such a problem. I mark minus 3. I look at the coefficient in front of these two brackets. I notice that there is a 1 here. I don't have to write it down, because if there's nothing in front of the bracket, then that's where it is 1. So I notice that there is 1 on the plus. It means that such a quadratic function is smiling, that it has arms up. We're looking for x's that are greater or equal than 0. These are these intervals, these parts of the graph. That is from minus infinity to minus 3, and from 3 to infinity. And closed on 3's, but remember that minus 3 may not be closed. So the domain of the function will be all x's belonging to the interval from minus infinity to minus 3. Open, because minus 3 cannot belong here. And from 3 to infinity, note that 3 is closed, minus 3 is open. It means that 3 belongs to the domain of the function. Minus 3. It should be remembered that minus 3. We eliminated with this second equation. So let's move on to task 5. Here it will be quite easy at the top. The numerator does not interest us at all, because whatever there is, everything is correct. However, at the bottom, we have to solve such an inequality x minus 4x plus 3 has to be greater than 0. It cannot be equal to 0 because this polynomial, this quadratic function, is in the denominator. So we can't equate it to 0. We can factorize it. I do it this way. Here I look for the product, and then I add the numbers that I multiply here, and check what comes out. So I see that here is a plus, here is a minus. So it's probably minus 1 multiplied minus 3, and here minus 1 plus minus 3. Which means x minus 1, x minus 3, greater than 0, since I already have a quadratic function written in the product form. I can draw an axis, mark 1, mark 3. Pay attention that when I take out zeros from the product form, I take them with opposite signs. Here was x minus 1, the 0 place is 1. Here was x minus 3, the 0 place is 3. In front of the bracket, there is a 1. The function is smiling, that is arms up. The interval that interests us is this interval. And this one. So the domain of this function is x, which belongs from minus infinity to 1, or from 3 to infinity. Let's move on to the next task. Here is quite an interesting task. We have here as if a function consisting of 2 parts. Here in the first part, we have a function under the root. In the second part, we have a function that has some binomial in the denominator. We have to consider both and find their common part. So we know for sure that 5 minus x must be greater than or equal to 0. And x, I made a bad correction. X squared minus 1 should be unequal to 0. Here, we can see immediately that this is our difference of squares, x minus 1, x plus 1. Not r equals 0, so x not equals 1, and x not r equals minus 1. Here on both sides we can add x, and it will come out that x is less equal to 5. What happened here with this record? 1 added x plus 0. Pay attention to the beak of this minority. It is directed towards x, because when we add x here, it will be 0 plus x. Will be here on this side. So I rewrite x, the beak is directed as before towards x. However, if you look here, this open part of this minority is towards 5. So here is the same. So now I have firstly the interval and two exclusions. I can draw it as standard on the number line. I mark all these numbers -1, 1, 5. X have to be less than or equal. That is, I blur the 5 because the 5 belongs to interval. And all x's that are earlier, except here, I make an open circle. And here I make an open circle. This means exclusion of 1, -1. So the domain of this function are all x's that belong from -infinity to 5. Close to, but without a two-element set in which there is -1 and 1. You can write it like this, or with the help of three sets that is from -infinity to -1, from -1 to 1, and from 1 to 5 closed on the right side. However, this notation, in my opinion, is a little faster and easier to understand, because we calculated everything nicely here. Again, let's move our task to this place here. I am approximating. And we can continue counting. We were on task 6, let's move to the 7th. So we see that in the numerator we have x minus 2, which has to be greater or equal than 0. In the denominator we have x squared minus 9, which is not under the square root, so it only has to be not equal to 0. It follows that x minus 3x plus 3 does not equal 0. So x cannot be equal to 3, and x cannot be equal to minus 3. Here on both sides we can add 2. And we know that x have to be greater than or equal to 2. As standard, I draw an axis. I mark 2, I mark 3, I mark minus 3, all x's that are greater than or equal to 2. And minus 3, I have to open and open 3 as well. Pay attention that the fact that minus 3 is open, and as if it is excluded from the domain, does not interest us at all. It is somewhere there outside our interval. Our interval is from 2 to infinity, and with an open 3, that is excluded 3. Apart from that, minus 3 does not interest us, so let's write down the domain, where x belongs to the interval from closed to infinity without a single element set in which there is 3. Let's move on to task 8. Firstly, in the numerator, whatever happens, we are not interested, because the numerator could even be 0. Here it cannot be, so even more. But here there is denominator either, so we do not deal with the numerator. However, in the denominator, we have 4x squared, which must be exclusively greater than 0. It cannot be equal because the denominator cannot be equal zeros. Now, first of all, let's pull out the minus in front of the bracket, then we have x minus 4. Secondly, let's use the shortened multiplication formula, writing it down quickly. Now, let's draw a number line, minus 2, 2. In front of the bracket there is a minus. Means that this is minus 1. Therefore, the quadratic function in such a product form is sad. That is, its arms go down. It goes this way. What we are interested in is the interval above 0. That is above the line symbolized by the x-axis. In this way, our domain of the function are all x's that belong to the set. from -2 to 2. Let's move on. We have such a problem. Let's shift a bit. We have such, we can write it this way: x minus 1 by the square root of x minus 4. So it follows from this that from the numerator, it results that x minus 1 has to be greater or equal to 0. Additionally, x squared minus 4 has to be only and exclusively greater than 0. We can quickly solve plus 1. That is x greater than 1. And this we can write x minus 2, x plus 2. We see here that we have a quadratic function, minus 2, 2. In front, as they say, there is one. So the function is, the quadratic function is smiling. We are looking for numbers that are greater than 0. So these are these numbers. So additionally, we know that x's have to be greater than 1. Greater equal. So we paint over and let it go in this direction. Then we are looking for the common part of this interval. So from minus infinity to minus 2, and from 2 to infinity, and the interval from 1 close to infinity. This is this part of the graph, so the domain of this function is xs, which belong from 2 to infinity. And finally, we have the last task. We know that x squared minus 6x plus 9 has to be greater than or equal to 0. Besides, we know that x squared, 1, cannot equal 0. From this equation after writing it out using the formula. It results that x cannot be 1 and x cannot be minus 1. So this is the easier part. Here, however, we notice the formula of shortened multiplication again. There's even a formula that I showed in the example. So we can immediately put into the form of a square of a binomial. Greater than 0. To visualize it on the axis, we mark this 3. Quadratic function which lies here, it looks like this. The vertex has an 3. And we are looking for all numbers which are greater or equal than 0. So in fact here, all xs belong to this quadratic function. Why? Because this quadratic function, which has 0 placed precisely in 3, has arms above the x-axis. And the vertex at the point precisely 3, and we want all values which this function accepts, which are greater than 0. So all points belonging to the arms are above 0, so they belong. And the vertex which lies on the x-axis, which has a value equal to 0, also belongs. So only 1 and minus 1 does not belong to the domain of the function. We can write it. 10 belongs to all real numbers. But without previously disabled minus 1 and 1. That would be it. If you like this video, leave a like. It is very important for the development of my channel. If you want more such videos, subscribe. Stay up to date. And of course, I invite you to support my channel. Once again, thank you for watching. Until the next one.